Thank you. Thanks, Chris. Thank you all for coming. I'm honored that you came. I'm going to try something. Actually, two things are new here. I'm going to try a little bit of this and a little bit of that. I'm going to talk about a subject I actually haven't talked about in public before, which is nice, because it's brand new. And so I'm going to begin with cosmology. I'm a little hesitant always to give after dinner talks, especially when people have been drinking. But anyway. But the point is, cosmology is such an easy topic. It's not bothering me yet, Adam. Okay, I'll let you know. But, you are, but it is. But the point of cosmology is it takes you away from all those really important things. So the first part of the talk, you better look at the wall there, because the first part of the talk are going to be slides, and then I'm going to talk about some things I've been thinking about with education. But so. Cosmology tells us a story about the universe that takes us out away from those petty worries we have nowadays. And in many ways, today is really, as I want to point out, really the best of times in the current time. And of course, what I mean by that is that the Large Hadron Collider is about to turn on again. So that's very good. But at the same time, it's sort of the worst of times, as Charles Dickens would say. And you know, it's well, I don't have to say any more. But I want to take you back to a story that is really only about 3 or 4 months old, something I've been thinking about a lot. And it's amazing that what it may do is turn metaphysics into physics in a certain way. And I find it fascinating. So I think I entitled this A Journey to the Beginning and End of Time. And so here is a standard Hubble Space Telescope picture. This is called the Extreme Deep Field picture, one of the deepest images of the universe. So as you may know, in every dot in this picture is a galaxy, not a star. It's a small region of the sky, and because it's done in several different colors, you can actually see all the galaxies between about 8 billion years ago and the present. And the interesting thing about it is the universe is the same everywhere, as far as we can see. I mean, there are these little lumps called galaxies, but there are about as many galaxies in that direction as that direction. And that's a real mystery. We don't understand why the universe is the same everywhere. And to try and understand that, we want to look back in time. We want to look further and further and further. Because when we do cosmology, we're doing sort of cosmic archaeology in a sense. Because when we look out at stars, as they say, these small galaxies here, especially the bluer ones, are maybe 8 billion or 10 billion light years away. And that means the light from those galaxies took 10 billion years to get to us. That means the light was emitted 5 billion years before our sun even formed. Okay? And most of the stars in this picture don't even exist anymore. They burned out. So we look back, we are getting a picture back in time. The further away we look, the farther back in time we're seeing. Now, in principle, you would imagine that means if the universe is 13.8 billion years old, which it is, not 6,000 in case anyone is wondering about that, then you would think if you look back far enough, you'd actually see the Big Bang. And that would be true, except we can't see all the way back to the Big Bang, because earlier and earlier in the history of the universe, it was hotter and hotter and hotter. And at a certain time, when the universe was about 300,000 years old, it was so hot that neutral matter couldn't exist any longer, that every time a proton tried to capture an electron to make an atom, it would be broken apart. And you had this charged plasma, and you can't see past the plasma. So if we look out as far as we can see, oops. I don't know how this works here. I'll try and... They gave it to me and it wasn't working right either. There we go. Let me try it this way. This might work better. Okay, is that better? Good. Okay. So if we keep looking back further than this time, which is, as I say, this is just 8 billion light years, 10 billion years ago. We want to look back almost to the beginning of the Big Bang. We can look back up to the point where the universe was only 300,000 years old. And when we do that, we see that surface where the universe suddenly became transparent. And we see radiation coming at us from that surface 13.8 billion light years away, more or less, in all directions. Because once protons were able to capture electrons, once the universe cooled down sufficiently, suddenly it became transparent. So just if I look at this room, I can see the walls, because the air is transparent all the way to the walls. If we look out, and if there was a Big Bang, we should see radiation coming at us for all directions. And that radiation was discovered by accident in New Jersey, of all places, by two people who didn't know what the hell they were doing. And they won the Nobel Prize, because you don't have to know what the hell you're doing to win the Nobel Prize, as I tell my friend Brian Schmidt here all the time. But they discovered radiation coming from the Big Bang. And now we can take an image of it, and we can actually look back at that primordial universe. So this is the best current image. This comes from the Planck satellite. This is an image, it's like we take an image of the Earth, which is a sphere, and project it on a plane. This is an image looking out in all directions, projected on a plane. This is where our galaxy is. And so if this is looking up and this is looking down, and we are looking at, these are primordial hot spots and cold spots in that microwave background radiation, which represent essentially the lumps that would later on collapse to form all those galaxies. These are the primordial seeds of everything we can see, and us and everything else. And now we can, and at least 2 Nobel Prizes have been given for that. Actually, better than this image, we can take away the galaxy, because it's not so interesting. And when we do, we sort of get this image. And this is what the early universe looked like. Little hot spots and cold spots that represented overdensities and underdensities of matter that would later collapse to form clusters of galaxies and stars and planets and people and aliens and everything that exists right now. Great. So that used to be as far back as we can see. 380,000 years after the Big Bang. The primordial universe. Oh yeah, it's still in the ground. Okay. Yeah, here we go. Okay, I'm going to really have to fix this now to make it really work. So, up until about 6 months ago, when I talked about how far back we could see, this is how far back we could see. And the reason is, the universe becomes opaque before that time, so we can't see back before that time. But, if in principle, we could look back further if we could find something that interacted more weakly with matter than light does. If we could have some signal from the very early universe that would propagate through this plasma of radiation and matter and make its way to us, then we could see the beginning of time. And what is amazing is in the last 3 months we think we've seen the beginning of time. We're not certain, because first observations in science are often wrong. But it sort of smells like it and looks like it, and if it walks like a duck and quacks like a duck, it may be a duck. So what are we using to see back earlier in time? Well, light interacts relatively strongly with matter. What is the weakest force in nature? That was a rhetorical question, but some of you answered it anyway. It's gravity. Gravity is the weakest force in nature of all the forces. And Einstein told us, first realized, that just like when you shake an electron, you produce waves of light, electromagnetic waves. In general relativity, every time you wave your hands, and I wave my hands a lot, you are creating a gravitational disturbance. And gravity is nothing other than the fabric of space-time. So every time I move my hands, I'm disturbing space-time. And that disturbance propagates out at the speed of light, just like an electromagnetic wave does, and we call it a gravitational wave. And so anytime you are moving, you're creating gravitational waves. But gravity is so weak that we've never been able to detect them. So what does it look like? I think this next image is, okay, there we go. When a gravitational wave comes through this room, what it does is it changes the length of the room. In one direction, the room gets smaller, and in another direction, the room gets larger. It shrinks space in one direction and stretches it in another. But by a very, very small amount for most, when I move my hands, the gravitational waves that are produced are so weak that the disturbances in this room could never be observed. But if we could measure gravitational waves, what we'd see, basically, is literally space changing. And then this is sort of a projection of it as it comes through, and if you want to see what it would actually look like in 3 dimensions, It's kind of a neat little snake-like thing. When a gravitational wave comes through, that's what's happening to space. It's a wave of space-time. And what's amazing is we've been trying to detect gravitational waves. They're very hard because gravitational waves are very weak. We built these amazing machines to detect them. And so this is the largest detector of gravitational waves on Earth. This is called the LIGO. I think it's the Large Interferometric Gravitational Wave Observatory. But what it does, and it's got two arms. One arm there, one arm there. They're about 4 kilometers long. And this is amazing. This is why I like experimental physicists so much, because I would never want to dream of that you could do what they can do. I'm a theorist, so it's easy. If a gravitational wave comes by the Earth, what it will do is it will change the length of one arm compared to the other. Because remember, in one direction, space gets stretched. In another direction, space gets squished. So what is done here is that laser beams are projected in both directions. They bounce off mirrors here and come back. And so the light takes a certain amount of time to get to there and a certain amount of time to come back. And if the length of one of them changes relative to the other, there'll be a time difference between where they come back. Okay? And you can try and measure changes in length. Now what is remarkable is this is a 4-kilometer long tunnel. And what these experiments are designed to do, and what they can do, is detect a change in length of one of the arms of that interferometer compared to the other. The 4-kilometer long arms, they can detect a change in length by 1/100th of the size of a proton. It's amazing. 1 part in 10 to the 21st of the length of that thing. 1/100th the size of a proton. You'd never dream that that's possible, but it is possible, and they've been able to do it. They still haven't seen any gravitational waves. Because even if 2 neutron stars in our galaxy collide, about the most catastrophic phenomena you can imagine, the gravitational wave that comes by is so weak that it changes the length of those interferometers by less than 1/100th the mass of the size of the proton. They're improving this detector, creating an advanced LIGO, and being able to, in fact, improve the sensitivity by at least a factor of 10. So 1/1000th the size of a proton. And there we predict, that when neutron stars in our galaxy collide, they may produce gravitational waves. Now, in fact, there's lots of noise. When trucks go by 100 miles away, they produce a bigger signal in just the vibration of the road. So you have to be very careful and and do an amazing job. But one way you can check is to have 2 of these things. So there's one of these in Washington State and one of them in Louisiana. And if a large gravitational wave comes by from some distant region of our galaxy, it'll produce an effect in both of them at more or less a time difference, which is just the light travel time between Washington and Louisiana. And so if they can see the same vibrations happening in space, and in those 2 places, it'll be good evidence. There's also a lot of work being done here in Australia, by the way, in gravitational waves. In fact, we have to use what are called quantum optics, and a lot of interesting work is being done at a variety of universities here in Brisbane and ANU and a few other places to try and develop the techniques to make these gravitational wave interferometers. But we've never seen gravitational waves directly. But it turns out there's another source of gravitational waves that's stronger than anything that this is looking for. And it's the universe itself. Because if we go back to the beginning of time, when the entire observable universe, everything we can see, all 100 billion galaxies, each containing 100 billion stars, was compressed to a region smaller than the size of an atom, the densities, the energy densities, were so amazing. I mean, you can't even comprehend if you try and think about that. Imagine all of that mass, all of that energy in a region the size of an atom. The kind of phenomena that happened then would generate gravitational waves that might be detectable. And here's where we now are looking for them. Not in nice, hospitable Washington State, but this place here, the South Pole. Here is a detector. In fact, it's a detector that looks at the cosmic microwave background radiation, the radiation I showed you earlier that comes from 380,000 years after the Big Bang. And this detector is called the bicep detector. Here it is. Actually, it's kind of, I love this picture because this is taken at sunset, which happens once every 6 months. Because once the sun sets, it doesn't come back up again for 6 months. So this is the last time you can see light in Antarctica at the South Pole. And these experiments are done, in fact, largely in the winter at the South Pole when it's very cold. And this microwave receiver looks at that radiation, but it looks not for the hot spots and cold spots, it looks for something else. Now I'm going to show you the next image is very complicated. It's from a Scientific American article I just finished that's coming out in about 3 weeks. But I want to walk you through it. And since an artist drew it, and I'm better than my drawing, I chose it. So this is a picture of the history of the universe. This is the beginning of the universe. This is today with lots of galaxies. At the earliest moments when the entire observable universe was contained in the region about the size of an atom, that's right there. We predict, based on our ideas of particle physics, that something very strange happened back then, at that instant. The energies were so immense that the universe underwent something called a phase transition, like when water freezes to ice. And in fact, if you're on a day when it suddenly gets cold very fast, there's water on the roadway, it can be below 0 Celsius and it still won't have frozen. Okay? Because if the temperature changes very fast, the material gets stuck in this metastable state, the liquid state, and then suddenly it freezes. When it does, it emits a lot of energy. It turns out our ideas of the early universe are almost identical. We think that as the early universe expanded, it got stuck in a metastable state. We call that period inflation. And energy got stored in empty space. Back then, when the universe was a billionth of a billionth of a billionth of a billionth of a second old. Okay? A billionth of a billionth of a billionth of a billionth of a second after the Big Bang. We speculate. We theorists can speculate about whatever we want, and no one, it's easy to do. But we predicted that would happen. The universe would get stuck, and when energy gets stuck in empty space, the universe starts to expand incredibly fast. And the prediction was that in a billionth of a billionth of a billionth of a billionth of a second, the universe would expand in volume by a factor of 10 to the 90th. It would go from being smaller than the size of an atom to being about the size of a soccer ball. In a billionth of a billionth of a billionth of a second. Okay, fine. But during that time, when the universe is expanding, the energy densities are incredibly high. And gravity, which is incredibly weak, we predict that at those incredible densities, quantum mechanics is important, and it may even be important for gravity. And space-time itself may begin to fluctuate by quantum fluctuations. Those quantum fluctuations produce disturbances in space-time, but the universe is expanding so fast that those get frozen in. Instead of vibrating, they get frozen in because they get stretched to be larger than the size of the visible universe, namely their period. So they would like to oscillate like gravitational waves, but the universe stretches them so their period becomes longer than the age of the universe, and they just sit there. So you have these quantum fluctuations in early time that get frozen in, and then after inflation ends, they're observable as gravitational waves. Now the first ones to get stretched get pushed out the longest. The last ones to get stretched just before inflation ends come and start vibrating first. But as gravitational waves start vibrating as the universe expands, they dissipate their energy. So the shortest wavelengths, gravitational waves, dissipate their energy, and by the time the cosmic microwave background is formed, they've gone away. But the longest wavelength waves, the ones that are just beginning to oscillate, when the universe is 380,000 years old, what do? Well, remember, the cosmic microwave background is formed when the universe becomes transparent, the last instant before protons capture electrons. So just before it becomes transparent, you have these free electrons sitting there. If a large gravitational wave comes by, it'll shrink space in one direction and stretch it in another. And what that means is the electron will see a hotter universe in one direction and a colder universe in another direction. and it will scatter that radiation to us, and we'll see it today, and that radiation will be polarized. It'll be stronger in one direction than another. Many of you have polarized glasses. And what polarized glasses do, light can vibrate, and electromagnetic fields can vibrate in many different directions. And the polarized glasses cut out one direction of polarization that comes from scattered radiation on the ground, which is why you can see through, if you're a fisherman, you can see through the water better, because that polarization gets canceled out. But what we predict is if there were gravitational waves created at the beginning of time, they'd produce a very particular kind of polarization in the radiation. And what this experiment in the South Pole was designed to do was look for this kind of snake-like pattern of polarization. And actually, no one thought anyone would see it. 4 months ago, the experiment reported a result. And here's the actual data from the experiment. You see exactly what we predicted. This snake-like pattern of polarization, of twisting polarization in the cosmic microwave background. There's cold spots and hot spots, the ones you saw before, but on top of that we've shown the polarization, the direction, if you wish, of the electromagnetic field that's causing that radiation to come to you. We can measure it in this detector, and it was exactly what was predicted if inflation happened in the early universe. Now, we don't know if it's really a gravitational wave from inflation. In fact, there's a lot of discussion, because there are other things that could produce this kind of, like anything that's very sensitive, there's lots of noise that can produce it. It turns out there are polarized dust grains in our galaxy that emit polarized radiation. And some people have argued that these people may be seeing is just some foreground effect from the radiation coming through our galaxy. But it looks identical to what we would predict. And if it really is a gravitational wave from inflation, the consequences are profound. Because not only does it mean that for the very first time in history we've detected gravitational waves, we see them literally in the image. But this image comes to us not from 380,000 years after the Big Bang, when the hot spots and cold spots came from, but the polarization is due to gravity waves that have been traveling from the time the universe is a billionth of a billionth of a billionth of a billionth of a second old. If this is really true, what this is an image of is an image of phenomena that took place at essentially the Big Bang. And that changes everything. It increases by a factor of 10 to the 49th our ability to go back in time. More than any era in the history of humanity, it allows us to jump back and test what the universe was like when its physical size was less than the size of an atom. And we can test physics that we thought we'd never be able to probe, ever, empirically. And I want to just spend 2 minutes, even though I spent longer than I planned, I think, talking about this, but I want to just tell you a few of the things we can test. Now remember, I told you that inflation, if it happens, and by the way, if these gravitational waves are real, that tells us there's this crazy idea that the universe expanded by 10 to the 90th in volume in a time period of a billionth of a billionth of a billionth of a second. That's really right. And what caused inflation to happen, I'll remind you, is a phase transition. When the nature of the laws of physics, if you wish, change. Now, we know, in fact, that such phase transitions have happened later in the history of the universe, because we've discovered there are 4 forces in nature: electromagnetism, the weak force, the strong force, and gravity. And we discovered that 2 of those forces, electromagnetism and the weak force, were once unified at a certain time. It turns out when the universe was a billionth of a second old. And in fact, that's the physics that the Large Hadron Collider has been able to test, that idea. The Higgs field is a manifestation of a phase transition that caused 2 forces which initially looked the same to suddenly look different. And we discovered the Higgs particle, so we know that happened. But we've predicted that maybe all the forces of nature at a much earlier time came together. And in fact, if we measure the strength of the forces of nature, the electromagnetic force, the weak force, and the strong force, it turns out they have very different strengths now. But if we go up to very, very much smaller distances or higher energies, it looks like the strength of those forces are coming together. And we can measure them, and we've discovered that if all we see now is everything there's no new particles in nature, then the forces of nature don't merge together at a single point. But an idea was proposed that maybe there are new particles in nature due to a mathematical symmetry called supersymmetry. And the beautiful thing about that is if you suggest that at the scale, which might be probed at the Large Hadron Collider, suddenly there'll be a whole new bunch of elementary particles that will appear, then when we do the mathematics, we find out those forces unify at precisely an energy scale 16 orders of magnitude more energetic than the rest mass of the proton. Which means the physics corresponds to a distance scale 16 orders of magnitude smaller than the size of a proton. Now, if you imagine that happens, and there's a phase transition associated with that single unified force suddenly splitting into three forces, that will produce inflation at this scale. And if you ask, what would be the strength of gravitational waves that might be produced by inflation at this scale? It's exactly the scale we measure of the gravitational waves that have been seen at the South Pole. If this is true, we are suddenly able to measure physics, particle physics, on a scale 1,000,000 billion times more energetic than the Large Hadron Collider. To build an accelerator that could probe particle physics on that scale, it would have to be larger in radius than the Earth-Moon distance. We'll never do it. It will never happen. If this is true, we can now use these gravitational waves to test the laws of physics on a scale absurdly small. Now, what's interesting about this is, if this is true, then we would expect in the Large Hadron Collider to see a lot of new particles. But there are other things we might expect. There's another amazing device, and as I say, experimentalists do amazing things. This is a tank of water, 50,000 tons of water, located in a deep mine in Japan, Kamioka, Japan, with 11,000 phototubes. And it turns out that if I go back, and I think I can go back this way, yes. If the forces of nature come together at this scale, it turns out that diamonds aren't forever. I'm sorry to let you know this. But it turns out that elementary particles like protons are unstable. And a proton will decay. It will decay with a lifetime of 10 to the 35 years, which is about 1,000,000,000,000,000 times longer than the current age of the universe. So you don't have to worry. You don't have to sell your diamonds right away. But you can say, well, how can we test that? Well, if the average proton decays in 10 to the 35 years, if you have 10 to the 35 protons together, on average, you might see one decay each year. So all you have to do is get 10 to the 35 protons. Where can you get it? 50,000 tons of water. This detector has been sitting underground for 20 years in the dark, waiting for protons to decay. If these gravitational waves come from inflation at this scale, this detector will see a proton decay. And as I say, if those gravitational waves come from inflation at the Big Bang, this is CERN Geneva. If you've ever been to Geneva, you land at that airport, you look out, you see farmland. But under the farmland is the largest accelerator we've ever built, the Large Hadron Collider. It's 26 kilometers around. It goes across us from Switzerland to France about 26,000 times every second without a passport. And in fact, it's currently down, being improved. But when it turns on again next year, it's designed to look for these particles that come from supersymmetry. We have built the largest devices that humans have ever built, the Gothic cathedrals of the 21st century. If you're ever there, you feel like Gulliver. These are humans back down here. This is one of the small detectors. It's called the compact muon solenoid. It's a really small detector. There's more metal in that detector than there is in the Eiffel Tower. This is one half of this detector. The other half is on the other side of this image. Each of them weighs 20,000 tons. They're not on rollers, but the magnetic field is strong enough when the detector turns on that if they weren't already put together, the magnetic field would bring them together. And we accelerate particles in a superconducting environment 26 kilometers around to try and measure collisions that produce these new, we hope will produce these new supersymmetric particles. This is a sister machine, a much larger device. A human is down there. Okay, and this is the other large detector. And if we have seen gravitational waves from inflation, then it is likely when the Large Hadron Collider turns on, both of these detectors will detect a whole new invisible world of particles, of supersymmetric particles, that were just products of our imagination, but may be real. So there's this incredible connection between looking back in time and looking at the fundamental scales. If we are really seeing the beginning of time, we are going to probe nature on scales that are unimaginably small, and maybe get to the issue of the beginning of our universe itself. Because if inflation happened, it turns out it doesn't turn off so easily. So not only will we predict that we'll see new particles of the Large Hadron Collider, we predict that in fact our universe formed when inflation ended. But it turns out most of space, if we're right, is still expanding. And now, somewhere else, so far away that we'll never be able to see it, another universe is forming because that region is leaving inflation. It's like ice crystals forming at different places. So if we can actually test that inflation happened, we know there are other universes. We will know that there are other universes. Universes we'll never be able to see directly, but we can be certain exist because we can test the physics that predicted them. Just like in 1900, we could be relatively certain that, 1905 actually, that atoms existed, even though there was no hope of ever seeing them. And so I wrote my book, The Universe from Nothing. I talked about a multiverse, the possibility of many universes. And people say, well, my theological friends, of which I have none. No, that's not true. They say, well, you and I, as I said, you probably heard me say in Melbourne, in the Atheist Convention, they say you invented the multiverse because you don't like God, which is true. But that's not why we invented it. We were driven to it. But they say it's just like religion. I mean, how can you say? Well, the difference is we can test the ideas. And if this is true, we can argue that the multiverse really exists and that our universe is just one of many possible universes. And the galaxies we see in our universe have a particular characteristic, but in other universes they could be quite different. And the laws of physics that we now have may just be an accident in our universe, because if they're any different, we wouldn't be here. And some people who are religious argue, well, that's fine-tuning. This is God. Everything was fine-tuned so we could be here. But that's exactly the wrong thinking. The point is, it would be very fascinating to find ourselves living in a universe in which we couldn't live. That would really be worth an after-dinner talk. Because it's just like cosmic natural selection. If we can only survive in a universe with these laws, it's not too surprising that we evolved in this particular universe. Just like a bee wasn't designed to see the colors of flowers, but if it couldn't see the colors of flowers to know where to get nectar, it wouldn't survive natural selection. This is cosmic natural selection. So the last thing I want to point out is that if all of these ideas are true, I have talked about how miserable the future is. But it's more miserable still, potentially. Because if these ideas are true and the scales are what I measure, it turns out that the Higgs field, which now permeates our universe and causes us to be able to exist, may be unstable. And one day, it may undergo a phase transition, and then everything we see will cease to exist. So as my late friend Christopher Hitchens used to say, when talking about something from nothing, as he said, why is there something rather than nothing? When I told him about this, he said, well, nothing is coming at us as fast as it can be. In fact, if you wait long enough, there'll be nothing again. So the answer to why is there something rather than nothing is just wait. There won't be for long. So that's the future. It is potentially more miserable than you can ever imagine. But the good news is, if the Higgs field is going to undergo a phase transition, you won't know what hit you. The whole universe will disappear, and you won't even know what happened because it'll happen at the speed of light anywhere. So drink up and be merry. That's the end of this talk. I'm going to spend 5 minutes talking, for those people who got lost in my first slide, I just want to spend a little time talking about something that is closer to home, especially here in Australia. So I'm going to change gears, if you don't mind, and then I'll answer, hopefully, cosmological questions and not political ones, but we'll see. I want to argue something here. I've just written an article, which it hasn't come out. In fact, I don't even know where it's going to come out yet. And I want to abstract some thoughts, because I've become convinced that we have to be a little bit stronger when we think about education than we do now. And I want to propose something which I know will cause ripples. I hope will cause ripples. And I want to quote Richard Feynman, who many of you know I was a big fan of. He said in 1988, which is the year before he died, he said, "Permit us to question, to doubt, that's all, and not to be sure. It's our responsibility to proclaim the value of this freedom, to teach how to doubt, how doubt is not to be feared, but welcomed and discussed, and to demand this freedom as our duty to all coming generations." And that's, in my mind, the call to education. We owe it to our children to educate them as best as we can. And what I want to argue is, that means the purpose of education should be to plant the seeds of doubt. To openly question falsifiable religious doctrine and give children a new chance to overcome the yoke that their parents are imposing upon them. And that's why the school chaplaincy program is more than bad policy. It's destructive to the well-being of our society, in my opinion. And there's a variety of reasons for this. So, in fact, there's some data. There was a recent study by social scientist Brendan Nine that was reported in the New York Times. And it provided evidence that if you confront evidence that deeply held beliefs, either religious or ideological, most people will reject the evidence. And the important thing is, more knowledge doesn't help. Knowing the answer doesn't help. Knowing the details doesn't help. Those who are better informed in this sociological study, those who are better informed about the issues, simply were better prepared to know what evidence to reject, to reinforce their ideas. So faced with this reality, how can we make progress on key ideas whose resolution must be based on empirical evidence, like climate change, for example? Clearly, what we do now in schools is not enough. Educating people about the facts is not enough. But providing a set of facts, I want to argue, is not the purpose of education, in spite of the fact that we tend to treat it as such. What the purpose of education is to teach people how to distinguish between fact and fantasy, how to derive facts by questioning and testing, and where to go to access reliable data. That's the reason why young scientists are so easily can reject what us old people are proposing, because they've been trained to doubt. That's what we do in science. We train people to doubt. And we can't falsify the vague postulate that there's purpose to the universe, even though there's no evidence of purpose in the universe. But the point is, there are many specific claims in Scripture, in all the world's Scriptures, that are explicitly falsifiable. And we shouldn't shy away from them. The purpose of education, I would argue, is instead of shying away from that, to openly point out those falsifiable claims and show that they're falsified. To encourage children to doubt the beliefs that their parents teach them. And there are lots of examples about falsifiable things in the Bible. We're not just talking about the vague crap like Jonah and the whale. I mean, the Old Testament is replete with really falsifiable assumptions. The most recent one is that, the many references to domesticated camels by Abraham, Joseph, and Jacob. And that was almost 1,000 years, as you probably have heard, before recent studies have discovered camels were domesticated in that region of the world. The people who wrote the stories were 1,000 years after the fact, and they talked about people using camels, but at the time people didn't use camels. A centerpiece, of course, of Muslim teaching and much of the Islamic claim to Jerusalem, it involves Muhammad's famous night journey by horse to Jerusalem to lead all the other ancient prophets in a prayer in a mosque there. There's a problem, however. No mosques existed in Jerusalem at the time Muhammad was there, but we never hear that discussed. Okay, not to mention the fact that there's no evidence he ever visited Jerusalem. And then there's the Mormons. The amazing thing about Mormon, and we almost had a Mormon president, okay, is that it's manifest, unlike that, it's just as stupid as the other religions, but it's manifestly falsifiable. Joseph Smith, of course, translated these golden tablets, as you know, which then disappeared. in the Book of Mormon, but he made a mistake. The Mormons bought 4 Egyptian papyri, along with a mummy, actually, and he translated them into the holy books of the law, at the base of the Mormon religion. One of them is the Book of Abraham. But they made a mistake. They actually drew the Egyptian tablets. And in fact, recently at the Museum of Art in New York, they were discovered. They still exist. The problem was poor Joseph Smith translated those tablets 2 years before the Rosetta Stone was deciphered, which now provides a lexicon to translate them. And so his Book of Abraham, when you look at it now, is just the burial rites of Ra. We know that. You never hear that discussed. I tried to write that in an article in the United States during the last presidential election. I couldn't get a single newspaper to publish it. By the way, I learned it from some ex-Mormons here in Australia who came to educate me, some former Mormon bishops. Now, happily, there are many places in the world where what I just said would produce decapitation. But in a rational world, it's hard to argue that we should not question openly in our educational system these ridiculous assumptions and encourage children to doubt the stories that their parents tell them. I would argue we not only have that obligation, but it's important. There's some other studies. A recent poll in the United States displayed a massive public unwillingness to accept the reality of human-induced climate change. There are only 33% of Americans are confident of human-induced climate change. 31% are confident of evolution. 27% are confident about the age of the Earth being 4 billion years and 4.5 billion years instead of 6,000. And only 21% were confident in the existence of the Big Bang, which, by the way, we can see. But more telling still is the demonstration in this survey of a direct correlation between religious conviction and an unwillingness to accept the results of empirical scientific investigation. As religious faith monotonically increased, confidence in the Big Bang, climate change, the age of the universe monotonically decreased. Religious belief genuinely appears to be an obstacle to understanding the world. And it's a disease that begins early. There was a new study that was just published this month in the journal Cognitive Science that exposed a significant difference in the ability of children as young as 5 or 6 to distinguish fact from fantasy, depending upon their past exposure to religious education in church or parochial school. The children with religious training were less able to judge that characters in fantasy stories were fictional rather than real, compared with children with no such exposure. That's why religion is child abuse. Ultimately, all of this matters because religious faith is not innocuous. As my late friend Christopher Hitchens put it so pithily, religion poisons everything. It's trite to argue that what people believe isn't crucial, it's what they do that matters, but religious beliefs govern actions, and they consistently translate into misplaced activities in all spheres of humanity, and that's one of the reasons why tomorrow I'm going to be at a protest for the World Congress of Families that is here. Okay, I want to skip to the end. That's why I'm advocating that as a matter of service to our children, we have to encourage public education to not be neutral, not to avoid religious training, but to in fact explicitly, as one of its main purposes, dispel myths by planting the seeds of doubt, by encouraging children to doubt the things their parents tell them and their teachers tell them. And it's not just in religion, it's in every area of human activity. It's an obligation that we have to the next generation. And that's why by making a special place for pastoral care in our schools, as Tony Abbott would put it, the Australian government is perpetuating the myth that religion should have a special place in our society, give special knowledge, and should be accorded special respect. That is child abuse. If we continue to shy away from the courage to directly confront myth and superstition with rational doubt, we risk a future that's no better than our past. And I want to close with Richard Feynman's plea, which he finished his article on. He said, "It is our responsibility to leave," and forgive me when he wrote this, he said, "the men of the future with a free hand. In the impetuous youth of humanity, we can make grave errors that can stunt our growth for a long time. This we will do if we, so young and ignorant, say we have the answers now, if we suppress all discussion, all criticism, saying, that's it, boys, man is saved. Thus we can doom man for a long time to the chains of authority, confined to the limits of our present imagination. And we owe it to our children not to do that. Thank you very much. So, that was something completely different. In any case, I'm happy to answer some questions. Yes, you had your hand up right away.
A couple of early slides, that beautiful Hubble deep field thing is of this stupidly small portion of the sky, is it not? Could you explain?
Yeah, oh yeah, I mean,
how small that is?
Were you the one who sent me that $2 coin?
No.
Oh, so who you were? Okay. Is this the reason you sent it to me? I don't know if you were. It was it a tip? In which case, I appreciate it.
It's because outside you were getting heaps of photos of people, and
someone said I should charge people for posing.
And then we were taking a photo, and then you came over.
Well, you all owe me $2 then. I thought it was for the following reason: if you take a $2 coin and hold it up in a region of the sky where it's dark.
I'm not as smart.
Well, that's why you do. This is where you pretend, okay? I do it all the time. If you held a $2 coin up in a region of the sky where there are no stars, and you looked at that same region with a Las Campanas telescope in Chile right now, an 8-meter telescope, you'd see about 100,000 galaxies. So you're not seeing 100,000 galaxies there. It's an absurdly small part of the sky.
It's like a match head.
It's like a match head. It's much smaller. It's very small because, in fact, because that allows them to look very deep.
And when you hold a match head at arm's length in the sky, there's a whole lot more of those match heads left around you.
By the way, if you're interested in the ability of these telescopes, not this telescope, but the newest large telescope, which Australia is part of. In fact, I'm at ANU part of my time, and they're a part of something called the Giant Magellan Telescope, which is being built in Chile, and it's about 25 meters across. It'll be one of the largest telescopes in the world. Its ability to detect light, it could detect a firefly on the moon. Okay, just so to have you a sense of the kind of stuff we're doing
The
nowadays.
second one was that beautiful map of the background radiation in all those false colours. How there was no scale. How hot and you said hot and cold.
You're right.
You said hot and cold.
I want to take more time.
How hot and how cold.
That's amazing. The fluctuations are very, very small. The hot spots and the cold spots differ by 1/1000th of a degree. The background itself is 3 degrees. It's a thermal background of 3 degrees. The difference in hot spots and cold spots is a little less, actually about 1/10,000th of a degree. That's why it took so long to find it. That's why the people who found it won the Nobel Prize. The second set of people, because they knew what they were doing. Yeah.
I'm very interested in this phase transition of the Higgs field breaking down.
Yeah.
Would you have any better in any way calculate how long it would take to happen?
Well, no. It depends a lot on whether supersymmetry exists.
Would we ever be able to find this out?
Well, yeah. I mean, the point is that if we have a fundamental theory, we can calculate if the field becomes unstable and what the average time it should take for it to decay. But we don't have a fundamental theory yet. We've discovered the Higgs, but we don't know why the Higgs has the mass it has. One of the reasons we think maybe this idea of supersymmetry. So that's what's very exciting, is because this points out the possibility, very real possibility, that the Large Hadron Collider will discover supersymmetric theories. If that's the case, we will have a much better handle on a fundamental physical theory of the Higgs, and we'll understand whether, in fact, it's unstable or not, and we'll know how bad the future really is. So there's a possibility of actually knowing, in principle, the average time it would take for a universe to decay. But, of course, let's say the average time is 10 billion years, okay? That doesn't tell you anything, because the universe is quantum mechanical, okay? It may mean our universe will decay in another 5 billion years. It could decay tomorrow, or it could decay many times later, because quantum mechanics says there's only a probability. But right now, we don't know the answer. But what is amazing is, if you ask, where is the borderline between a stable Higgs and an unstable Higgs, it's very close to 125 times the mass of the proton. The Higgs that we measured is 125 times the mass of the proton. And so it's right on the hairy edge. If it was much lighter, we'd know the answer. Much heavier, we'd know the answer. It's right on the hairy edge. It's amazing. Maybe there's some profound reason for that. We don't know yet. All of these are amazing questions that we may be able to answer, which is even more exciting. Yeah?
Yeah, I was at the Atheist Convention and I noticed one of the other speakers had a lot of security and threat.
Yeah.
And the right of free speech and threat, and how you've had an observation of people and friends that have been subjected to threat because of their free speech. I want to have a perspective of what your thoughts of free speech versus hate speech is. And I think it's I'm a bit confused about what I could ask, but
Well, I
you
mean,
have a different experience.
I'll tell you what worries me is not free speech, is hindering free speech. Okay. In fact, one of the things I didn't say here is a lot of people say, what do you care about any of this stuff? There's these global issues. But I get letters every day, and so does my friend Richard Dawkins. I get letters every week from people whose lives are destroyed because they doubt. I got one 2 weeks ago from a 27-year-old who happens to be growing up in the U.S. after Saudi Arabia. He watched his father executed by family members. Okay? Another one was a 15-year-old in a Muslim-dominated school who wanted to be a scientist. And he told me, what they write me is that science has liberated their mind because it realizes they realize they can ask questions. So the real problem here is that people who are so damaged psychically by the fact that they just want to ask questions. That's the real problem with religion, is that it tells people that asking questions makes you a bad person. So I'm more worried about the restriction on free speech. As far as hate speech is concerned, I think I have very little constraints on what people should say. Because from my point of view, I've debated, for example, I don't believe in debating people a lot, in spite of the fact that I've debated an idiot here in Melbourne a while ago. But every now and then. I had debated this guy Ken Ham a long time ago, who's also Australian. Sorry. Yeah, I know. You send them all to the U.S. What can I say? But I debated him at a better moment. It was the day the museum opened, and I was in fact leading a protest about the museum, and then that night I had to fly to New York City to be on a Fox News program and debate him. And my feeling was, he started to talk, and I thought, just don't say anything. Because let this guy talk. Because it's so ridiculous that it will, and so I kind of feel in situations like this, you let people say what they want to say. And then you have the courage to confront them. But confront them by not confronting them as people, but the things they say. That's what I tried to do with William Lane Craig.
Okay. My issue is the hell threat. Once you say, I have hell for you, you dehumanize somebody and it gives you the right to harm somebody else.
Well, I mean, that's the real problem. The only place I've ever, and I don't have, there have been one or two times when I've had bodyguards. The only places that I've ever been assigned bodyguards, I've never asked for them. Let me make that clear, unlike my friend who was at that convention always travels with them. But the only place, was that?
She had very high level.
Yeah, okay. Ayan Hirsi has real threats. There's another friend of mine who's there who has imagined threats.
I knew that because of my experience and my contacts, I knew she had an active threat.
Oh, she has them everywhere.
But she had an active threat in Melbourne.
Oh yeah,
because I've met prime ministers in Melbourne. I've never seen an active threat in Australia ever.
Well, that's the problem. She had the misfortune of being born Muslim, and happily I didn't. And my Jewish friends, don't try and kill me because I laugh at them. But the difference, what I want to say is the only place I've ever been assigned bodyguards, the only times I've lectured that I've been assigned is when I've lectured to religious groups, which says something to me. It's amazing that the only places that people fear for my safety, and it's not just Muslim groups. Sure, in London I was assigned bodyguards, but the very first time I debated William Lane Craig was in North Carolina before I knew anything about him, for a Campus Crusade for Christ event. 25 police at every door, because they thought, and then as I started making jokes, by the end of the evening they left, but I think that says something when people feel the only place that your health is threatened is when you talk to people who are religious. It's really, that says something, doesn't it? Yeah, in the very back.
Yeah, the picture you had of the multiverse, I know a picture is just a very simple
just a
model.
picture, yeah.
Do we take that to imply a finite size of the universe, or are we still saying impossible to tell at the moment, it looks flat, it looks infinite as far as we can measure it?
Well, if our ideas are correct, our universe, it does probably have a finite size. Much larger than the observable universe, because we can only see out as far as light can take us. If our ideas are correct, our universe actually has a finite size, but it's embedded in what could be an infinitely large universe, multiverse. So there could be an infinite number of finite sized universes. There can even be an infinite number of infinitely big universes, because infinity is a wonderful thing. And so those are questions which sounded like metaphysics, and they have been. But what is fascinating to me is that we may be able to get an empirical handle on those ideas. And who would have imagined that we, sitting here in this random, boring suburb, not Melbourne, but where the sun is around the Milky Way, will be able to answer those questions in our lifetime. That's what's the wonder of science to me.
Do we have a minimum size then based on the current level of flatness that we've measured?
Oh yeah, well it's certainly it's larger than 10,000 times the observable universe. Okay. Oh, more questions. Yes.
Can I suggest that, the issue of religion in any society, we're a world of many different peoples, and
Yes.
perhaps to defuse conflicts, we need to learn about each other. So perhaps rather than banning religion, we need to have comparative religion. And then all of these religions will eventually fade into being cute kind of lessons of history rather than reality.
I agree with you, but of course I think we should expose children to that, but we shouldn't expose it when there are classes of comparative religion.
We don't have any in
Well, there are in the U.S., but they're presented as if they're all sacred. What we need to do is present comparative religion as a bunch of interesting historical anecdotes, and then and show the silly reasons why they did what they did. But absolutely, instead of shying away from it, we have to explicitly educate people to confront their own misconceptions.
I think that might be a century away. I think in the interim, at least if we learned about each other, we would be less likely to want to kill each other.
Well, you know, when you say it's a century away, when I talk about this, and it was again something I cut out from my remarks because I was going late, people say, well, you know, religion's been around since the dawn of humanity, you'll never change that. But I point out, and Nancy and I were just talking, we talked about this a lot, this issue of gay marriage, it's going to go away. Because if you have a child, we have a 13-year-old, they can't understand what the issue is. It's it's gone. One generation is all it takes. So I can tell you that, you know, a generation ago people had said there's no way that people would allow gay marriage, okay? And slavery, essentially a generation got rid of it. And so all you have to do, change is always one generation away. And we have the children, and exactly. So if we can plant the seeds of doubt in our children, religion will go away in a generation, or at least largely go away. And that's what I think we have an obligation to do. Yes, you gave me the $2, so you got to ask a question. It's another $2 though.
I only got one. I already checked. I'm sorry.
It's all right.
I think the fear for me is that medical science is getting that progressive that, you know, one generation doesn't last 90 years, or it might not last 90 years. And
It takes a long for people to die, yeah.
So the premise of, you know, the generation gaps is...
Yeah, that's true. In
You
fact,
know what I mean? Like, if old people are living to 200, then are their ideals being carried along with them?
well, you know, that's true. There's a statement that old theories never, in science, that old theories never die, old theorists do. And if it's true, you just have to wait for them to die. But you're absolutely right. But the question is, who has the positions of power in a society? And ultimately, it's going to be the next generation. That happens. And so, the best we can do is try and make the next generation better than this one. And that's what I think we all try. That's what the purpose of education is.
Can I add?
Uh-huh.
The oldest woman on the planet, the oldest person on the planet is currently 116 years old. She was born in 1898. When she was born, there was an entire whole other set of people on the planet. Everybody on the planet has changed in that time.
Yeah.
We all
It's just,
have
we,
changed that
you know,
generation.
death is a wonderful thing.
I made the suggestion that if part of the core curriculum for every student was logic, critical thinking and comparative religion, they'd all wake up that all of these contradictory and mutually exclusive belief systems can't all be right, but the logical conclusion is that they're all wrong.
You know, you're right, but I mean, I think that's right, but I'm against sort of teaching logic in that sense as an abstract thing, because kids always wonder why the hell they're learning whatever the hell they're learning. So to me, in order to teach it in a way that kids will internalize, you have to convince them that it's related to something that they're interested in. So you could take, and it doesn't have to be science. All fields of scholarly endeavor, in principle, deal with the same kind of critical thinking, examination, all because I happen to firmly, I was going to say believe, but I don't use the word believe. I know. No, I don't know. But I highly suspect, from the basis of everything that I know about the universe, that the only kind of knowledge is empirical knowledge. That you can take any discipline and use it as a way to teach critical thinking. So you don't teach logic in the abstract, because I think kids will it'll go in one ear or the other. But you demonstrate to kids their own misconceptions by asking, you know, this is really true, so I'm happy to crunch up a picture myself, okay? Is that someone? Oh, it's not you. Okay, I better not do that. This is your notes. I can crunch them up. Okay, so
That's okay, you can use that.
no, this won't break. I hope. It's a rock. Okay, so I did this for the leaders of the free world once when I was lecturing in Aspen. So I said, got a piece of paper and a cup. Okay, I'm going to drop them. Which is going to hit the ground first? Well, you'll be pleased to know that the leaders of the free world all agreed the cup would hit first, and it did. And it did break. I used a book in that case. But what I then did is what I do for first-year physics students. I took the piece of paper, I did this, and they fall the same way. Okay, and so all of them had gone in school and learned that Galileo told us that all objects fall the same rate in the absence of air, but it had gone in one ear and out the other because it didn't mean anything. But when I did that demonstration to them, it confronted their own misconceptions, caused them to think about why they thought what they thought, and I guarantee you that all of them remember it. Okay, so that's how. If you want to teach kids, you can't just tell them things. You have to do it in a way that brings them in ways they're interested. And it doesn't. And as far as I'm concerned, it doesn't matter what field. I don't care what you teach them, whether it's physics or in some sense history or any area. You're teaching those very tools. But you don't shy away from religion any more than you shy away from the claim that the Earth was the center of the universe. We laugh at that now, and we explain to kids why that's, we get kids to realize why that might be wrong, or that the Earth is flat, because we can go around it. And so we should take other falsifiable facts, which are the center of our society, which is religious doctrine, and make just as much fun of that as we do of everything else to get kids thinking. Anyway, that's it.
With religious education, it tells you what to think, not how to think.
Yeah, well, exactly. How to think is
absolutely a no-no.
Exactly. We should get kids. And by the way, what all teachers are also hesitant to do, as parents are, is to convince kids to not believe what they say, to doubt what they say, because that's what good teachers should do, and that's what good parents should do too. But it's very hard to do. I'll go on this side. Well, yes.
I know of, and a lot of people experience quite spiritually profound, things throughout their life.
Yeah.
Unreligious, just purely spiritual. Do you think that can be sort of proven with science, or do you feel that there are still certain things and certain realms and dimensions that people can experience that will never be proven with science?
Well, science doesn't prove anything. Let me make that clear. That's the biggest misconception about science. Science can only prove things to be wrong, not right. Okay? If it's, the Earth isn't flat. How we know we go around it. Okay, so it's wrong. But just because an idea satisfies the test of experiment doesn't mean it's going to satisfy the test of all experiments. So science doesn't prove things to be right. If you're asking me, are there many things in the universe we don't understand? Absolutely. That's why I'm a scientist. Because there's lots of things left to understand. There's a lot more we don't know about the universe than we do. But what people confuse when I say that is they confuse that with the assumption that because there's a lot more we don't understand than we do, that we don't understand anything. But there's a lot we understand. And the spiritual things, if you want to call them that many of the exotic phenomena people experience, in general, violate the things we know to be correct on the basis of experiment. So they're highly likely to be wrong. And so I can't say to someone who's heard God in their ears that they're not hearing God, but I can say it's much more likely that you're hallucinating, based on what we know. In fact, again, to quote Feynman, when he's talking about aliens, he said, I think aliens are much more likely to be due to the known irrationality of humans than the unknown rationality of aliens. Because it's much more likely. If you look at the likelihood that a spacecraft could come to the Earth, almost anything you could think about is more likely. And what science deals with is not true and false. It's likely and less likely. And some things are just so unlikely that they're not, that you chalk them off. And so I can't tell someone that what they've heard or what they've seen or some mystical experience, but I can say it can be a coincidence, a weird coincidence. But none of us like to believe that the things that happen to us are coincidences. We all are hardwired to believe that things that happen to us are significant. And like you believe, you have the illusion that what's happening to you tonight is significant. And it isn't. And for that reason, I'm going to take only one more question because I don't want to waste any more of your time. But I think I'll take yours since you're close and you might.
Okay, I'm going to take two questions. One that's terribly naive. Gravitational waves, if they cause expansion and contractions in certain points in space, what effects does that have on time?
Oh, okay.
Yep. And the second question relates to the. I've got to prefix this by I'm fascinated, horrified, and charmed by Hypatia oyster shell that you're wearing.
Who's the gentleman who gave me this? You want to stand up? Where are you? He gave it to me because he asked me to wear this. This is in honor of the.
I find
3 weeks ago, I had the thing on my Facebook. All the beheadings and the Israeli stuff was happening, right? And I was
You know the story, so I'll give you
I was really distressed, and I wanted to make a symbol against religious violence, and the amnesty symbol with there's the candle and the thing, and Hypatia was the last classical philosophy character at the end of the classical, about 400 AD, and she was killed by radical Christians before they burned the Library of Alexandria, and
They killed her by flaying her skin. Someone else told me it was abalone shells, so I'm not sure.
Yeah, it might have been. Yeah, but I got the oyster shell and the match because they burnt the library down, and put her name on the match, and I also thought with if someone was gay, they could put a sign about that, and the thing is, I realised you'd been in this new organisation about secular
Global Secular Council, maybe.
And therefore I thought that's the best meme I've ever had in my life, and the privilege of you wearing that, and potentially that becoming the symbol of against religious violence and the repression of knowledge would be...
well, that's why I'm wearing it tonight. It's not going to last very long.
It's not going to last very long, but it's actually...
I think it's a story I didn't know, and so it's a wonderful...
Yeah,
I
but
appreciate
it might be an idea that gives others... Silently, you can say, I don't like people hurting other people because of their beliefs.
Absolutely.
And I think we could all stand up and say
Now, it does lead you on to point out, of course, that she was a sincere and practicing pagan.
Yeah, absolutely. Paganism.
And this does come to my question. There are a number of religious atheists out there, people who join religious organisations because they enjoy the community and so forth. I mean, you're talking like a good percentage of the Jewish populations. You're talking about 2/3 of Unitarians.
I suspect most people who claim they're religious are in fact just that.
Almost certain of that. Is there not a role in the educational system which follows that historical perspective that says this was a contribution to human knowledge which has got a continuing tradition? Rather, falsifying dogmatic, foolish things, in the same ways that we sort of had a bit of a giggle at Greek myths or any other myths. do you still see a role in that sense where people are actually coming together? to
Okay,
talk
well, I
about
remember
the
that
issue?
question. I forgot your first question.
Oh, gravity waves and time.
Okay, gravity waves, the simple system.
Yeah, the physics
much
one.
easier.
The physics one.
Gravity waves are much easier than any of this stuff. The answer is yeah. I mean, space and time are connected. So if you distort space, you distort time. Just like my watch is now ticking slightly faster than your watch. It's because I'm slightly higher than you in a gravitational field. It's a consequence of general relativity. So and we can measure it, and we do measure it. In fact, you all measured it if you came here, because GPS systems wouldn't work if we didn't take that into account. So that's simple. The other question is much harder, I think. Absolutely, we have to ask why religion has been so ubiquitous, and it obviously has a cultural and sociological and to some extent evolutionary perspective. And so of course we should discuss that and ask the question, why is religion basically in every human culture? And understanding human cultural evolution, understanding what religion provides in terms of not just community but power, organization, many things, is a very useful thing to do, and a lot of colleagues of mine study that, and it's really fascinating to think about why that's the case. And some people will say, well, religion is ubiquitous, and therefore there's some truth to it. But you know, it just demonstrates some aspect of humanity. It doesn't mean, because it just, the great thing about nature is, one of my favorite science fiction writers wrote that reality is that which continues to exist even when you stop believing it. And that's the difference between reality and religion. Thank you very much.
Well, thanks a lot, Lawrence. We've really enjoyed the evening, and I think we're leaving here tonight with a few questions answered, and we've got, you know, we can go back a few more fractions of a second, you know, in terms of our knowledge of the stuff we didn't know before.
Two things. One, I did promise some of you I'd sign books, which I'll do. And the second thing is I hope that you have, it's not so much that you have fewer questions answered, but I hope you have many more questions to ask.
I just wanted to mention our, you know, we generally have an event once a month. We usually charge $4. We were a little bit more game this time around. But I just wanted to give you this, Lawrence, in a very spontaneous kind of way.
Thank you very much. We'll drink that tonight. Thank you very
Well,
much.
I'm sure you will.
Thank you very much. It's been a real pleasure. Thank you. I appreciate it.
Thank you very much for the two of you for coming along from Canberra tonight. We've really appreciated it.
Thank you.